to talk about e-commerce database in the cloud. And it's working, excellent. You know, one of the nice things about being in fashion is you do something called a high-low. You know, you'll wear something very expensive and you wear something not as expensive and you get a nice look. So I'm going high with the iPad and low with the piece of paper here. You can tell they work for me. So to keep my PR folks happy, I'd give you a quick rundown as to what ideeli is. We are a leader in the flash sales space. We have over 4 million, mostly women, online. We announce sales, pretty much every day at this point. Our premium members come in at 11. Our non-premium members, who make up the vast majority, come in at 12. It is an extraordinary experience. The company has been growing very, very rapidly. I'd say last year was 460% year-on-year growth. The previous 2 years, 600% each, which is running about 20% month-on-month growth, which as a CTO makes life very, very interesting. I believe we're going to make these slides available afterwards through Percona. So there are some things that we're going to go over very quickly here because we want to leave time at the end for questions. And if you have any questions, raise a hand. There are 2 of us here, so one of us can pay attention and watch the crowd. So a couple of interesting stats, again, and this is going to be the absolute end of the slides provided by my PR group. The most important here, or there are a couple of them actually, 149 add to carts per second, right? And at a sustained rate, we do over 50. So this leads to a set of challenges that you don't typically see in most commerce environments for companies our size. If you're Amazon, you see them. If you're, doing, only several hundred million a year, you typically don't see them, except maybe around Christmas. And this is why you care, right? So this is a graph of queries per second, right? We peak out, is it 24,000? 24,000 queries per second, 80,000 requests per second coming into the web farm. And this is over a 400 gigabyte production data set. So I think one would characterize this as a fairly large database. It is being accessed fairly frequently, which leads to lots and lots of fun. I was quoted actually in a Percona paper as saying this is a self-created denial of service attack every day. So we get to test our code. It's good. So this is one of those things I'm going to gloss over. Only in as much as we could spend an entire day talking about this, and there's a gentleman in the room who spent more than one creating it. Luckily, it wasn't me. We're going to zoom in a little bit here into a much smaller stack. So you can see web requests come in. We're using Ruby on Rails, which many of you will be familiar with, but if you're not, the semantics of using it are similar to a PHP type stack. It's share nothing, process-based concurrency. In our case, we're running Apache with a system called Passenger, which is very much like mod PHP, and that reaches out to the database. Each one of these instances reach out to the database. They're accessing concurrently. They're doing very similar queries. It's important to know that we're doing a great deal of caching, and we will talk a little bit about that. That's probably a topic in and of itself. But we do as much as we can to make sure things don't fall through to the database, but plenty of them do, as we saw in the 24,000 queries per second. So, in our case, we're on Amazon's cloud. It's worth talking a little bit about, what makes up the term, sort of the various components, so you understand what we're talking about going forward. And now I'm going to yield the mic over to Aaron.
Hi there. So just talking a little bit about, we're going to use a lot of these words for dealing with Amazon's cloud. We got a nice drawing here. It's basically there's regions and availability zones, which define where everything lives in the world physically. Regions are equivalent to a data center. They're geographically distributed. Amazon has, I think, 5 or 6 now. There's one in Virginia. There's a data center in California. There's a few in Europe. And then within each data center, there's a kind of an isolated zone called an availability zone. I called it a pod here. It's theoretically protected from faults from other availability zones in the same region. Traffic between availability zones is very high speed, low latency. We tend to treat them, the traffic as not a concern going between availability zones. Between regions, you have to worry about security, you have to worry about latency and performance because you're dealing with the public internet. So any database calls that go over the internet have to be SSL encrypted. The big thing is that availability zones should be protected from failure. If there's a problem in one, it shouldn't cause a problem in the other. So there we go. Never used an iPad before.
That was your first time?
It was my first time. That's great. So one thing we want to talk about in reference to the server locality and how we handle disaster recovery is our replication strategy. I have a diagram up here of which kind of the important piece is that we have a master-master pair that's with replica slaves off of it that are each in a separate availability zone, so that if one availability zone just disappears off the map, which has happened, we're protected from failure and can do a failover to the secondary master. And then we also replicate out to completely separate regions, so in case something really bad happens and Virginia is no longer around, we still have our data somewhere. We're also doing some cross-availability replication, which you can see there's a arrow going from DB2 to DB-rep AD there, and then back across again, which is to protect our data sets across availability zones. Basically, stuff fails in EC2. It happens more frequently than we'd like to see, and the replication strategy needs to protect against individual zones going off the map.
Check, check.
Check, check, yeah.
Yep, no, this one's not working. All right. Now it is. 1, 2. All right. So it's worth noting that with our failover semantics, one of the very important things that we did early on is, well, actually, and we had to learn this the hard way, hence the kinesthetic learning, right? Active, master, master, really hard. You know, you need to be incredibly careful about how you develop your app to do that, and that wasn't us. So the important thing is, that master-master pair that Aaron just spoke about, only one is active at a time. And what we ended up doing is, after trying a whole bunch of whizzo cool techniques to fail over automatically if there's a problem, we ended up proving that active master-master at the same time is really hard. It breaks replication, and then once replication is broken, the value of your master-master pair is, well, quite limited. So we do it by hand. If there's a failover problem, pagers go off, and someone jumps in and changes the app. Now we've automated as much as we can the actual sort of repointing of the app, and it's quite a fast operation, but it's not a real-time operation. It's, you know, we're measuring that in minutes, not seconds. And it is a necessary evil with regard to the tools we have in the cloud now. What's interesting is that I had a previous deployment of a Rails stack when we had more control over the hardware and actually set up something kind of slick on FreeBSD with CARP that automatically would, you know, fail over, you know, in 2 pings. That is not an option for us in this environment. And it was a hard lesson to learn because we really wanted it to be an option. But putting the proxy in place, if you have one proxy, you have a single point of failure there. If you have multiple proxies, you end up in the multi-master-master active state. You know, it's just one of those things. It's statistically possible and eventually will happen. The beauty of distributed systems that get load.
So the other piece of technology I wanted to bring up with Amazon is EBS, which is elastic block storage, which Amazon had historically never had persistent storage. You had ephemeral drives, which when you shut down your instance or if an instance crashed, or the data just went away. It was gone. So they rolled out elastic block storage, which is great in that it provides a lot of flexibility. You can move drives around to different instances and do snapshots of drives. It's a very great technology, but there's some problems with it. It's slow. A single EBS drive, we can see, like I say 100 to 150 IOPS here, but it sometimes drops down lower depending on who knows actually what, because you don't have any control over that. The disk and network are actually shared on a single 1 gigabit link, which is on a multi-tenant system. So if you've got a smaller sized instance, you're not getting that whole gigabit to share between both your network and your disk. Disk latency is all over the place. It's very unpredictable, and that I suspect is caused by the network being shared in the multi-tenant environment. We've also learned recently that EBS can kind of fail in very unexpected ways. If you've got your own physical server, there's kind of a limited number of ways that a disk can fail, and usually it's just it went bad, or there's bad blocks. They're easy to detect. Those problems are much easier to detect. We found that's not exactly how things go down with EBS. And there's no performance guarantees. You can't say, I need 1,000 IOPS and get that. So what we've done, and it is becoming quite common, it seems, is we've rated a whole bunch of EBS volumes together using software RAID, just using MDadmin. And we actually use RAID 10. You would think we might be able to use RAID 0, and some people do with some success, but we'd get slightly better performance, but what ends up happening is we determine that EBS can kind of fail in really bad ways, and at this point we want to trust our data integrity to ourselves and not just to Amazon. We would assume, and we know that behind the scenes there's some redundancy in Amazon systems for your volumes, and data loss is not really common, but we want to protect against that as much as possible. Our main database servers have 10 rated EBS volumes on one and 20 on the other, mostly as an experiment, and we don't really see any performance differences between the 10 and the 20. So we haven't done any super hardcore benchmarks about it, but there seems to be diminishing returns after you get beyond 8 or 10.
So, one good way to make sure your database performs is to not touch the database. And in fact, when you have an application that gets pounded on as much as ours for brief periods of the day, it's absolutely critical. So, though it's one bullet here, it is an extraordinary amount of activity. We're at the point now where we're literally going and breaking into the queries generated by Active Record, which is the object relational mapper in Rails. Now, particularly for those of you who spend your life on the database side of that equation, you'll know that the queries that those things generate sometimes are suboptimal. But yeah, absolutely key to invest in, to basically have the proper measurement tools to understand where we're spending the time and then be able to pull it back out by changing the way it works. And I think we're just beginning that, and it's gotten very interesting, the level of lift we can get. The other thing is just caching, right? Now, sort of points 1 through 4 here, it's an interesting little path. It's basically a topic for another presentation, but it's worth noting that we're getting more sophisticated in how we cache and what we cache, but as that happens, and I think everybody makes this transition, the ephemeral nature of memcached becomes a problem, right? Because now you're realizing that you basically embodied, a year of processor time to fill up that cache. If it goes away, you have to regenerate, and that's kind of ugly. So we're moving into more persistent models of key value, eventually consistent caching. And I'm happy to discuss with anybody afterwards who wants to talk about this path. The one point is Membase. There wasn't anything wrong with Membase. It's just that the semantics of how they deal with failure were not what we needed, given the kind of, what we're using the key value store for.
stepping on stuff down here. So I want to talk a little bit about how we've tuned our servers and kind of the problems we've encountered. We were seeing these very frequent kind of mini stalls in our server they manifested themselves in very odd ways, but basically we'd end up with all the queries would just stop. We'd end up with hundreds of threads running concurrently for like 2 seconds at a time, and then it would just all flush through. And it was somewhat unexpected, and we didn't really understand why. We're dealing with very slow disk. You know, EBS is basically network attached storage. It's under the scenes. And as a result, we're widely, you know, the latency is very variable, and we're also dealing with multi-tenancy issues. If you have smaller size servers, you end up seeing steal time in your stats between other VMs on the same host. So here are a couple of things, just a few of the things we've done with some help from people at Percona. One of them is that we have just the biggest servers you can buy at Amazon. They are, you know, not enormous by any absolute standards, but they have 68 gigs of RAM and 8 virtual CPUs. And basically, when you have bigger servers, you're using up more of the host. So you have less multi-tenancy, and you just get more consistent performance. The more being the important part here. We've also, excuse me, bumped up the InnoDB log file size to be as large as it can be. We were finding issues where periods where we had lots of inserts, we were seeing these server stalls again, and this seemed to resolve the issue by kind of buffering and optimizing the writes. We've also turned the query cache off as a result of there was some heavy mutex contention going on that was diagnosed. So this is when we get the big pile of bills, the unmarked bills from Percona. But we enlisted Percona services a while ago. These are the lockups we were seeing here. Everything's going along. We had these, 40 millisecond response times from the entire stack, and all of a sudden, bam, you've got 1.5 seconds of a response time just from the database. And then it goes away. And during those periods, our throughput dropped to almost zero. So, maybe we were turning customers away, we don't know, but it still wasn't very good. So we enlisted Percona services to kind of help us diagnose that. Baron did a lot of work for us here. And, they were able to do things like quote individual line numbers in MySQL and when they were finding the exact source of the problem. Some of the issues they found, one was we were running into some mutex contention, both on the query cache and just in general in InnoDB. And as a result of that, they recommended we switch to the Percona server with ExtraDB. And it sounds kind of pluggy or whatever, but this graph is true. We went from having these just crazy variable response times back from the database to this nice smooth line. We were seeing heavy queuing on our front end, and all of a sudden, literally the day after we switched, all that queuing just went away after a fair amount of testing. We turned the switch and we upgraded one of our master DBs, and it was smooth as silk from there. So they actually ended up doing a case study on ideeli to kind of discuss the details of what happened here. Another thing unique to the Amazon cloud, at least, is they give you the ability to do some interesting ways of backing up your data. We've tried a few different things. One is just cold backups, so you just shut down the server, very traditional, and you just take a copy of the data and upload it to S3, which is their Amazon's storage service. That had particularly slow recovery time because you're dealing with it's fast, but not super fast download times to S3. One of the nice things that EBS gives you the ability of doing is doing just a file system snapshot. It's an atomic snapshot that just grabs your file system, and it takes hours in some cases to actually write. But you don't have to take your database down at all. You just need a quick lock on the database and all tables, and a quick lock on the file system. In this case, we're using XFS. And there's some tools that actually do that. One of them is EC2 consistent snapshot from Elastic. And this all works with EBS rated volumes as well. And we've had some recent issues where we've had to restore a number of these snapshots, and it works pretty flawlessly, except for you have a brief period of sync time required. The nice thing is the recovery time is almost instantaneous. You create a volume from a snapshot, like a 6 terabytes of data, and you have that volume available to you within 30 seconds, sometimes a minute, and you can attach it to a server. And if everything's configured the same, you're back up and running in 15 minutes.
So, for any of these sort of backup and recovery and disaster recovery setups, of course they need testing. And we got a little help from Amazon on this effort a few weeks ago when they had a major outage. Now, the semantics of that outage are well documented, and we're actually not going to go over exactly what happened to them. We're going to go over it from the perspective of our infrastructure.
Sure. So this is what Amazon had to say about it, and ultimately none of it's particularly important, as Mark was saying. For what matters is for us. I got a call at 4 o'clock in the morning from my coworker Sonny, who's in the office, and he said something. I don't know what it was. It wasn't really important at 4 a.m. I get those calls and I go, okay, I'll be on Skype. So I got down to my computer and things were bad. This is what we were seeing. So we would see, if you look at IOstat, we were seeing these stuck volumes that had no operations happening, but they were showing 100% utilization. And in fact, a lot of the servers that had these rated volumes, you couldn't even look at the output of MDstat to see the health of the RAID array. But you could see everything in IOstat. I could look at IOstat across these 20 volumes and see, these 3 are bad, or these 1. So basically what had happened is Amazon had a problem. Somebody pressed the wrong button, and about 13%, I think, was the number of EBS volumes in a single availability zone were affected, and were in this stuck state, which meant that for us, they were completely unusable. You couldn't do anything with them. It shouldn't have happened, but what we did have a problem was they had to turn off a few of the APIs for the other availability zones, which kind of contradicts the isolated nature of the different availability zones. So it made recovery a little bit difficult because we weren't able to move volumes around. We weren't able to create volumes from our snapshotted backups in the main zone. So let's talk about, also we discovered as a result of this that we had an additional benefit of the rated EBS volumes, which was we could yank some of the volumes out from underneath and recover the larger volume, which saved us in a number of places. We were actually down for about less than an hour, I think. All we had to do was do a manual failover to our other master database, and all of our production systems were back up and running. And that was as a result of the replication strategy we had laid out, which we'll go over here and talk about a little bit about what went wrong with that, actually. So basically what happened was we lost US East 1A up there. We had this cross-availability zone replica, which is in the X, dbrep AD, and then dbrep DA. And then we have our DR replica over here. So basically what happened is we lost a whole availability zone. We're like, okay, that's fine. We have our data. But what happens if something else goes wrong? And a lot can go wrong in the 4 or 5 days that this was affecting us. The problem was we had chained our DR node off of something that was in the affected zone. So we had crossed a replication zone and then gone back into a region. Now, if we'd drawn this out beforehand, we probably would have noticed that this wasn't a great idea. But hindsight's great, and what we ended up having to do is kind of emergency move one of our replicas over to slave directly off of our functioning master. That got us a data set that was still up to date, and if something else went really bad, we still had a consistent data set. We also learned that our bin log retention period was a little too short, and like after about 3 days of this outage, a couple of our reporting sets had to be rebuilt because reporting replicas had to be rebuilt because we didn't have the bin logs around anymore. So kind of a couple points about what happened. This was actually a data center outage. This is the type of thing that could happen anywhere, possibly with less downtime, but one incident comes to our mind, which was a little shorter, but was an incident at Rackspace a few years ago where a truck driver drove into a power grid, and they had all sorts of problems, and they were down for 12, 18 hours, something like that. You can look at this as a cloud failure and a cloud success. There's a lot of argument about how this fits in, but the big takeaway point was that the tools we were provided with the API in the cloud actually facilitated a rapid recovery. Once the APIs were turned back on, which was a problem, we were able to rebuild all of our instances, rebuild all of our volumes very rapidly, and the recovery period was actually quite short. I think the big takeaway about running in the cloud is expect failure. I mean, it's true everywhere. This isn't just a cloud thing, but you're going to have a problem. You're going to have an instance just disappear. You're going to have an instance crash. You're going to have volumes disappear. It will happen if you stay in the cloud long enough. The other thing is cache very heavily. Disk is slow. This is actually should not be on this slide, I think, but again, expect failure. It's going to bite you if you don't have your data distributed in multiple places. My recommendation is that if you need a database server, you actually need 2. They need to be in separate availability zones, and you probably want 3. You probably want another smaller server sitting somewhere in a completely other region as a just-in-case disaster recovery scenario.
Yeah, it's worth noting that this advice is easy to give and very hard to take. And the realities of sort of the financial implications and explaining to management, be it me or somebody less technical, that you need to spend 3 times as long because you need to set up these 3 instances and set up the replication strategy and whatnot. That's a difficult conversation. But I think if I had to boil this down to a couple of interesting semantics about cloud versus traditional data center operations, it's the variability is much higher. The ephemeral nature of the resources is much worse. The jitter and or variable latency much higher. So all the things that you might architect around, or you might kind of rely on the fact that, hey, I got great switches, I set up a brocade network, I've got the SAN. You can't rely on those. Now, in reality, you can't rely on those anyway because somebody will drive a truck into your data center one day. But but in the cloud, it's a much more frequent experience. This particular one was interesting in as much as it was a lot of correlated failure, which we didn't expect, but and it was bad. It also, Aaron touched on it, but it broke an abstraction boundary that Amazon had promised, that sort of the isolation between the availability zones. So what we thought would be our recovery mechanism, we had to really, there was a lot of quick thinking to move from, oh geez, we cannot spin up another instance right now, to, okay, let's repurpose and move things around and move within our environment, which is a much, I give credit to the systems engineering team that really moved quickly, and that less than an hour of downtime was also at 3 in the morning. So I suspect if that had been later in the day, it actually would have been tighter because, less bleary eyes. I get to take over here. So if 24,000 queries per second excites you and doesn't frighten you, please come talk to us. We're growing like mad. We need people across the spectrum, not just people who know databases really well. We also need developers and product people, et cetera. So the ideeli team, why don't you guys raise your hands, please? Hire. I sign your paychecks, hire. Yeah, so come find them or us. I'm here till noon. I think everyone else is staying, and I think we'll all be getting beers later. So love to talk to you a little bit about what we're doing. And with that, we'd like to open it up for questions. The gentleman 4 rows back there. I can't see your name tag, but yeah, you. Yeah.
Do you think you could predict or somehow compare page download speed between if you were just running your own iron as opposed to doing it in the cloud? Would your pages be 2 seconds downloaded with your own stuff, or 4 seconds with the cloud?
That's a very difficult analysis to do unless you've got both stacks set up somewhere. Let's just say at the moment we're aggressively evaluating our options in different environments than AWS. And we may be able to speak more intelligently about a question like that in the future. But there's so many variables. We focused on maybe 10% of that big architectural diagram that we showed. The other 90 impacts a great deal. And we're using CDNs, we're using all kinds of stuff. We're at the sort of size and scale where we can afford to write a check if we need to, and have in many cases to get better performance on the user side. The 24,000 queries per second is what falls through all that other stuff we've done to prevent it.
Clearly, that's an obvious question. You're in e-commerce, the faster the page loads, the comment flow.
Yeah, the more money we make.
The more money.
Yeah, I get to make that statement to our CFO all the time, right? So, yes, it's a great question. Some of the value of being in the cloud from my perspective, first of all, with the growth that I described, if I had to go write checks to provision machines, I would have been screwed long ago. So the idea of, okay, you know what? We're going to be on TV tomorrow, spin up 20 more front-end servers, and it's done, is great. That has been phenomenal for us. There was a period there for a while where we were varying the number of front-end nodes that we had based on time of day, because that chart that you saw from the beginning, we know that. That's known, we know it ahead of time, so we were basically putting these things in cron. What ends up happening as you get bigger, and I think, we probably have some people from startups in the room or projects that are growing, the sort of vast majority of your operation expense dollar starts dropping to the back end. Your databases get bigger, your message queuing servers get bigger, and whatnot. So then those are things that don't vary up and down. So the idea of going hybrid, cloud, fixed resource is an interesting one from a sort of financial perspective. And is there opportunity to get latency leverage? You bet, definitely. But could I quantify it? No, can't yet. So, question here?
You mentioned that it would take potentially a very long time for you to rebuild your cache there. How much data are you caching, size-wise?
How much data are we caching?
It's actually not. It's not an enormous amount. We dump our part of our cache every day, and then some of our cache data is rebuilt incrementally. We have a whole pool of servers that are dedicated just to keeping the cache warm. I think we have probably 6 or 8 Memcache nodes at this point, 7 or 8 gigs on each machine.
Yeah, I think it's important to actually think about when I was talking about computational time, not data, and the two are not actually all that related. So let's say, for instance, I was in the calculating pi to the billionth place business, then obviously that takes a long time to do, but then I might store one value.
Okay.
All right.
I'm curious as to what if you look into Amazon has an RDS service that is hosted
Yep.
MySQL, so I'm curious as to why.
They actually. So does everyone hear the questions, or do I need to repeat it? Okay, so let me repeat the question. The question was basically, Amazon has a service called their relational database service, where they run, they have a sort of MySQL in a box for you. Why are we not running that? We looked at it recently, but when they first of all, we came to Amazon basically right when they had come out with EBS, right? We basically said, okay, now they've got non-ephemeral storage. Great, now we can actually use it. Until then, I couldn't figure out a way to use it. So we predated it. And then when they first rolled it out in beta, we're like, that's great, it's beta, but we got a system that works. Why would I move to a system that might work? And then subsequently, we've done some tests actually. When I say we, I mean our friends at Percona, and we collaborated on doing some tests to see if it was better or worse. Now, in the end, what they're doing is what we do. They're rating EBS volumes under the covers. There are a couple of optimizations that it's sort of the classic Microsoft model. They've got access to a few APIs, we don't. But that didn't overcome the benefit of running our own environment. We actually found our environment to be significantly better, and I believe Percona blogged about it. Is that correct, Baron?
I started to, but held off until I could verify some more of the data.
Okay. Yeah, so our impression, let's put it that way, our strong impression at this point is that our setup from a performance perspective beats RDS. We'll have independent verification or non-verification sometime in the future.
Can you briefly talk about the REAC caching you're looking at?
So I'm going to keep this brief only in as much as we're in the middle of the prototyping phase, and this could veer off into a long and rambling conversation. But the reality of it is there's some stuff in the future where I see needing to be able to use sort of persistent key value storage as a valuable mechanism for generating dynamic pages. And getting back to the question before about Memcache, we're at this point now where it's moderately debilitating if Memcache goes away, because we lose all that work that we did to generate the caching. And now our server farm is not provisioned to just suddenly take that on as a immediate cache refill. So the semantics of REAC from a marketecture perspective are very nice around no single point of failure, the ability to have your data in multiple places, no master, no centralized master and whatnot. Those all look good on paper. We're going to find out in practice. There was a hand back here.
One small clarification on your failover slide. You had MySQL proxy in there, but you're not using MySQL proxy. Is that right?
Correct.
Is that disaster? I didn't know if that meant disaster recovery or using it with
I don't believe we're using it anywhere in the stack now.
No, not at all.
As far as you guys have your ER set up across regions, how much replication lag do you guys experience?
So actually, the question was replication lag. How much replication lag do we experience across region? And I don't know the answer.
Yeah, the answer is actually almost none. It's remarkably fast. I don't know if Amazon has magic or what, but once we got the initial data set over there, obviously, which took a few days, we don't see lag at all.
But I wouldn't rely on that.
Yeah.
It's not on the internet, right?
I'm sorry?
It's not on the internet, it's across regions, right?
Yes, it is. Yeah, we use MySQL SSL.
There's no Amazon magic.
Correct. Yes. They may have provisioned lines.
All right,
is
so
all, yeah.
we're getting the gong, but I encourage you to come up and find one of us, afterwards, we're around, and look forward to some interesting questions and conversations. Thanks for having us.
Yeah, thanks.